Divide and conquer. In section 2.3.1, we saw how merge sort serves as an example of the divide and conquer paradigm. We call that in divide and conquer. We solve a problem recursively applying three steps at each level of recursion. Divide, conquer, and combine. Divide the problem into smaller subproblems that are smaller instances of the same problem. Conquer the subproblems by solving them recursively if the subproblem sizes are small enough. However, just solve the subproblems in a straightforward manner. Combine the solutions to the subproblems into the solutions for the original problem. When the subproblems are large enough to solve recursively, we call that the recursive case. Once the subproblems become small enough that we no longer recurse, we say that the recursion bottoms out and that we have gotten down to the base case. Sometimes in addition to the subproblems, there are smaller instances of the same subproblem. We have to solve subproblems that are not quite the same as the original problem. We consider solving such subproblems as part of the combined step. In this chapter, we shall see more algorithms based on divide and conquer. The first one solves the maximum subarray problem. It takes an input, an array of numbers, and determines the contiguous subarray whose values have the greatest sum. Then we shall see two divide and conquer algorithms for multiplying and crossing matrices. One runs in theta of n cubed time, which is no better than the straightforward method of multiplying square matrices, but the other Strassen's algorithm runs in big O of n to the power 2.81 time, which beats the straightforward method asymptotically. Recurrences go hand in hand with divide and conquer paradigm because they give us a natural way to characterize the running times of the divide and conquer algorithms. A recurrence is an equation or inequality that describes a function in terms of its value on smaller inputs. For example, in section 2.3.2, we describe the worst case running time T of n of merge sort procedure by recurrence as in the given formula whose solution we claim to be T of n is theta of n log n. Recurrences can take many forms. For example, a recursive algorithm might divide subproblems into unequal sizes such as 2 by 3 to 1 by 3 split. If the divide and combine steps take linear time, such an algorithm would give rise to recurrence. Subproblems are not necessarily constrained to being a constant fraction of the original problem. For example, a recursive version of linear search would create just one subproblem containing only one element fewer than the original problem. Each recursive call would take constant time plus the time for recursive calls it makes, yielding the recurrence. This chapter offers three methods of solving recurrences, that is, for obtaining asymptotic theta or big bounds on the solution. In the substitution method, we guess a bound and then use mathematical induction to prove our guess correct. The recursion tree method converts the recurrence into a tree whose nodes represents the cost incurred at various levels of recursion. We use methods for bounding summations to solve the recurrence. The master method provides bounds for recurrences of the form where a is greater than or equal to 1, b is greater than 1. Such recurrences arise frequently. A recurrence of the form in equation 4.2 characterizes a divide and conquer algorithm that creates a subproblems, each of which is 1 by b, the size of the original problem, and in which the divide and combine steps together take f of n time. To use the master method, you will need to memorize three steps, but once you do it, you will easily be able to determine asymptotic bounds for many simple recurrences. We will use the master method to determine the running times of the divide and conquer algorithms for the maximum subarray problem and for matrix multiplication, as well as for other algorithms based on divide and conquer elsewhere in this book. Occasionally, we shall see recurrences that are not equalities but rather inequalities. Because such a recurrence states only an upper bound, we couch at solution using big O notation rather than theta notation. Similarly, if the inequality were reversed, we will use the lower bound big O omega notation. Technicalities and recurrences. In practice, we neglect certain technical details when we state and solve recurrences. For example, if we call merge sort on n elements when n is odd, we end up with the subproblems. Neither size is actually n by 2 because n by 2 is not integer. Technically, the recurrence Describing worst case, because boundary conditions represent another class of details that we typically ignore since the running time of an algorithm on a constant sized input is a constant. The recurrences that arise from the running times of algorithms generally have that often for sufficiently small and consequently for convenience we shall generally omit statements of the boundary conditions of recurrences and assume that T often is constant without explicitly giving values for small, and the reason is that although the changing value this is going over my head, but we'll try to keep up with it. We'll try to go on. We'll try to move forward. When we state and solve recurrences, we often omit floor ceilings and boundary conditions. Let us go to the maximum summary problem. Suppose that you have been offered the opportunity to invest in a volatile chemical corporations like the chemicals the company produces. The stock price of the volatile is rather volatile. You are allowed to buy 1 unit of stock only one time and then sell it at a later date, buying and selling after the close of the trading for the day. To compensate for this restriction, you are allowed to learn what the price of the stock will be in future. Your goal is to maximize your profit. Figure 4.1 shows the price of the stock over a 17-day period. This is the given figure information about the price of stock in volatile chemical corporation after the close of trading over a period of 17 days. The horizontal axis of the chart indicates the day and the vertical axis shows the price, same as given in this table, and the change is given. The bottom row of the table gives the change in price from the previous day. Positive value indicates a rise in the graph, while a negative value indicates a dip in the graph. Okay. Uh, your goal is to maximize your profit. You can't buy any day, you can sell at a later day, but you can only buy one stock per day, and you can. So what it means is this profit, this 13 is just 1 unit. You may buy the stock at any one time starting after day 0 when the price is 100 per share. Of course, you would want to buy low, sell high, buy at the lowest possible price and later on sell at the highest possible price to maximize your profit. But unfortunately, you might not be able to buy at the lowest price and then sell at the highest price within a given period. After day 7, which occurs after the highest price after day 1. This 130 is the highest price what they are trying to tell. You can't sell it after buying at day 7. You can't buy it at the day 1 price. You might think that you can always maximize profit by either buying at the lowest price or selling at the highest price. For example, you would maximize profit by buying at the lowest price after day 7. If this strategy always worked, then it would be easy to determine how to maximize profit, find the highest and lowest prices, and then work left from the highest price to find the lowest price prior. Work right from the lowest price to find the highest price price and take the pair with the greater difference. Figure 4.2 shows a simple counter example. Always start at the lowest price or end at the highest price. Again, the horizontal axis, and here the maximum profit of $3 per share would be earned by buying after day 2 and selling after day 3. The highest price of 7 after day 2 is not the lowest price overall, and the price of $10 after day 3 is not the highest price overall. Okay. Demonstrating that the maximum profit sometimes comes neither by buying at the lowest price nor by selling at the highest price. Brute force solution. We can easily devise a brute force solution to this problem. Just try every possible pair of buy and sell dates in which the buy date precedes the sell date. A period of n days has and by two such pairs of dates since uh, this is a combinatrix notation. What they are trying to tell us, let us take brute force solution is we start with day 0, we take this value starting value and we uh, may take the difference with all the other values, all the other days, remaining days. We store those values. Again, we start with day 1. We find the difference with day 1 price with the remaining days. We start with day 2, day 3, day 4. We store all the values. We find the maximum prices in those, maximum differences in those. So if you start with day 7, the maximum difference would be at day 11. And if you start with day 13, the maximum difference would be at day 16. And if you start with day 6, the maximum difference would be again at day 11, right? Combination of you are taking 2 days out of the n days given, or the simple intuition is that for n given days, for the first day you have n minus 1 pairs, for the second day you have n minus 2 pairs, for the third day you have n minus 3 pairs of differences. And for the nth day you have 0 difference. It would be summation of n minus 1, n minus 2 to n minus 0, or n minus n, I guess, 0. So this notation would be in combinations n factorial by n minus 2 factorial into 2 factorial, but with this our intuition, what we calculated, summation of n minus 1 till 1, right? So sum of the first 1 to n numbers is n into n plus 1 by 2, summation of 1 to n minus 1 would be n minus 1 into n by 2, or n into n minus 1 by 2, which is again same as what we got in the combinatorics problem. N factorial by n minus 2 factorial gives us n into n minus 1, and the 2 factorial in the denominator remains. So basically the total number of pairs would be n into n minus 1 by 2. N into n minus 1 by 2 is gives us the n square term, so it belongs to theta of n square, and the best we can hope for is to evaluate each pair of dates in constant time. This approach would take big omega of n square time. Can we do better at transformation in order to design an algorithm with small o, little o of. Theta is a 1 second, I am confused right now. Big O is the upper limit, right? Growth of functions. So here we are seeing that O notation is the upper limit, and omega notation is the lower limit. So when they said so can we do better? The lower limit would be n square time. Can we do better at transformation in order to design an algorithm with little o of n square running time? So this is a tightly bound thing. It is not loosely bound like big O notation. We will look at the input in a slightly different way. We want to find a sequence of days over which the net change from the first day to the last is maximum. Instead of looking at the daily prices, let us instead consider the daily change in price, where the change on the day I is the difference between the prices day The table info shows these daily figures in the bottom row. For each row as array shown in 4.3. All right. The table shows these daily changes in the bottom row. We treat this row as the array A. We want to find the non-empty contiguous subarray of A whose values have the largest sum. We call this contiguous subarray as the maximum subarray. For example, in the array of figure 4.3, the maximum subarray of 1 to 16 is the A8 to 11. Thus, you would want to buy the stock just after day 8, that is after day 7, and sell it after day 11, earning a profit of $43 per share. First glance, this transformation does not help. We still need to check summary for a period of n days. Okay. I'm not understanding the logic. The change in stock prices as a maximum summary problem here. The summary with sum 43 has the greatest sum of any contiguous summary. Let us see the intuition. Alright, coming back to here. When the change is high, let us take a sequence of numbers. When the changes are positive, the values are rising. So day 7 to day 8, the value rose. Day 8 to day 9, the value rose. Day 10 to day 11, the value rose. Okay. And there might be some dips in the value.